Welcome to Module 3, Lesson 3, where we will be writing products as sums and sums as products. Okay, we are going to be using area and some rectangular array models along with the distributive property, something we've seen before, to write products as sums and sums as products. Okay, which maybe sounds confusing, and but hopefully not. Okay, so if you're writing a sum, 4 plus 4 as a product is actually 4 times 2. Okay, and then 3 times 1 is, well, that's not a good one, huh? Let's see. How about 5 times 4 is the same as 5, or yeah, 5 plus 5 plus 5 plus 5. Okay? All right, so that idea. So we are going to, of course, it's not going to look like that, but we will be doing this products as sums and sums as products throughout, along with a bunch of other things. Okay? And of course, we'll be working with expressions and hopefully recognizing that when you rewrite an expression in a different form, it could shed a little light on the problem and how the quantities in it are related. Okay, so all of this is to hopefully make all of this material a little more word, a little easier for you. Yikes. Okay, here we go. Okay, well, in this opening exercise here, we are instructed to solve the problem using our old friend, the tape diagram. Okay, tape diagram is back. Yippee-dippee! Okay, so a sum of money was shared between George and Brian in a ratio of 3 to 4. Yes, our friend the ratio is also back. Okay, so we have George and Brian are sharing this sum of money. The ratio is 3 to 4. Okay, so let's just keep it in order here. We got George, here we've got Brian. Okay, ratio of 3 to 4. If the sum of money was $56, how much did George get? Okay, so we are going to look at this tape diagram wise, and if you want to, go ahead and give this a whirl yourself first. Go ahead and do that. Just pause and do it. If not, you want to just wait for me, you can just continue listening. Okay, so let's go ahead and do this with a tape diagram. So, and we're going to use these ratio values here. So if we do a tape diagram for George, he has 3 pieces for every 4 pieces that Brian has. Okay, so here we have George. And here we have Brian. Okay, so tape diagram wise, we have 3 for George, 3 for Brian. Okay, very, very important thing here is that each of these blocks here is worth the same. Okay, very, very important. Okay, that these are worth the same. Okay, each a separate block, and we can see, of course, that Brian is getting more of this money. Okay, because he's is getting 4/3 of it actually, and poor George is getting just 3 to 4. Actually, he's getting 4/7, and George is getting 3/7. But we'll look at that some other time. But anyway. You could just see the tape diagram shows you that George is going to get less money than Brian. Okay? All right, so we set it up that way. All right, now the question asks, if the sum was $456, how much did George get? Okay, so this is what we're interested in solving. This is the question we are interested in answering, which is real important because very often, you guys will come up with some answer which may be right if a different question was asked. Okay, so you need to answer the question at hand. Okay, so here it is. George and Brian. Okay, what else do we know? Well, we also know that these two together equal $56. Okay, so all of this together equals $56. So with that in mind, and also keeping in mind that each and every one of these blocks are worth the same, we can recognize that we have 1, 2, 3, 4, 5, 6, 7 of those blocks. Okay, 7 of those blocks. If they're all the same, we can very simply divide this 56 by 7, because there are 7 units. Okay, and therefore each unit is going to be worth $8. Okay, so per unit. Okay, and there we go. And that, my friends, is all we need. Now that we know that each unit is worth $8, we can plug them in. 8, 8, 8. That's all we really care about is George. And George gets $24 of it. Okay? $24 to George. Okay, and if we want to, here's Brian. 8, 8, 8, 8. And Brian gets $32. But we weren't asked to answer that question, so we don't really care. What we do care about mostly is George. Maybe we are George's family or something, or we're friends with George. Okay, so that's it. Maybe you did this yourself, and hopefully you got it right. Doing it tape diagram wise. Okay, now this example 1 has several steps, and I just would like you to follow along as I go through these steps, getting closer and closer to the point they're trying to make. It may not seem so obvious at first, but bear with me, or bear with them, as both you and I, or all of us together, try to figure out how this is going to make our lives easier. Well, anyway, so first of all, they would like you to go ahead and represent 3 plus 2 using a tape diagram. So if you want to just like zoom ahead of me and do this, you can, and you can always pause me and try it yourself first, but I'm not going to pause at all. I'm just going to keep going. So if I do that, I can very simply do this. 1, 2, 3, and then 2, and here I go. I have my 3, and here I have my 2. Okay. Now this can also be drawn differently. You could draw it that way, or let me see. I'm going to go ahead and no, I'm not going to. I don't want to select that. I'm just going to do that. I want to just actually copy this little piece here. I can't copy that. Okay, I was trying to copy and paste it, but so that 3 plus 2 right there can be like that, but you could also draw it this way. Okay, so now you need to visually see what this. You need to compare it visually. Okay, so you can actually see this 3 plus 2, and this 3 plus 2. Okay, are the same, just shown a bit differently. Here we've actually just taken apart, taken the median lines out there. Okay, well, let me just draw them side by side. So 1, 2, 3. Okay, 3 and 2. Okay, so those are both representations of 3 plus 2 using tape diagrams. Now, now they want us to go ahead and represent x plus 2 using a tape diagram. And this is going to look very, very particular. So here we have x. Now these two here, of course, need to be the same size, okay, because they are the same size. Now this x is going to be longer, and it's not going to, not going to be any divisions here. But they would like us to note the size of the units that represent 2 in the expression right here. So here are the size of these. If we look at the size of these, okay, and, and then we look at the size of this large one, excuse me, the x. Can you predict what the value of x represents? About how much? Okay, and it may not look what it's supposed to. I should probably be a little bit longer here. I haven't done this very well. Nice that they gave this to you too in your binder. Okay, well, if you don't know, that's fine, but it's approximately 6 units. Okay, all right. So if we say this is going to be, this represents x plus 2. The x is unknown, okay, at this point, but it's approximately 6 units if we look at it, okay. And these two up here are both 3 plus 2, just drawn in a few different ways, okay. Alrighty, so let's see if I have the next page here to go to. Next page is going to look like this. Now, what we want to do is we want to take that, this one here, actually this model here. We're going to use these 3 plus 2's, but now we're going to multiply by 3. We're going to multiply the whole thing by 3. So again, I would, and as a rectangular array, now it's no longer a tape diagram, but it's more or less several tape diagrams on top of each other. So if I went and did my first 3 plus 2, 1, 2, 3, 4, 5, here's my 3 plus 2. Okay, I have mine, that's my tape diagram. And now, if I want to times it by 3, I will just go ahead and do another one on top, and then another one on top of that. Okay, so now I have what's called a rectangular array, and you can see here's my 3. Okay, so I have, and again I can maybe, let's just go ahead and shade this in. So we shade in our 2 portion. Okay. Alright, so there we go. We have our 3 right down here, plus 2 right here, and then times 3, because they're all stacked on top of each other. Okay. Alright, now, just as for comparison's sake, let's go ahead and take our x plus 2, and this right here, this would look like this, 3, as you can see up there, 3 times 3 plus 2. Okay, and now if we take our x plus 2, okay, here's our x plus 2. Go ahead and, oopsie, sorry. Shade that in there, there are 2. Alright, and then if we multiply that times 3, do the same as we did over there, we are going to stack another 2 on top. Alright, so here is again, that was a rectangular array for 3x plus 2. Okay, here's our x, here is our 2, here is our 3. Okay, so these rectangular arrays are showing us now, they're taking a tape diagram and stacking them. Okay, so now we are able to use a multiplier. Okay, so now we're going to use this last array here, the 3 times x plus 2, and we're going to go ahead and erase these lines. Okay, these lines here, and then we're going to erase these lines. Okay, because what we know now is we want to start looking at these rectangular arrays like this. We want to look at them and just be able to label them with numbers, okay? Not have to rely so much, because we'll start using some larger numbers, not rely so much on using, the grid, such as this one up here, okay? So all we have to do now, if we've drawn this up to look like this, and it looks pretty much to scale. Of course, we can't draw things to scale ever. It's very difficult unless we're using grids. Just by virtue of the fact that we know this is 3 up and down here. This represents x across to this whole entire white rectangle, and then this is 2, represents 2 units there. We can represent the different areas, okay? This area right here is 3x because it's 3 times x, okay? And that's the area, okay? So we are now calculating the area of this rectangle right here, okay? Now the area of this rectangle, the purplish or lavender rectangle, as you can see, is 3 times 2, which is 6. Okay, so here we go. Each area is now represented by a term. Okay, and we've used the dimensions of the rectangular array to determine these terms. Okay, so what we've just done is we've actually just partaken using rectangular arrays and tape diagrams. We've partaken in what's called, and what we've come to know, and we have been talking about, I'm just going to get these out of the way right now, as the distributive property. Got to make these a little smaller here. The distributive property, okay? And so the distributive property can be written as in the as the identity of this right here. A parentheses B plus C equals AB plus AC for all numbers A, B, and C. Okay, we're just saying that there are 3 different numbers. You have your multiplier here, and then you have whatever lies inside of your parentheses, your parenthetical expression right there. And the way that looks here is you can see it right here. Okay, there is our expression, and from our expression we took that 3 and we multiplied it by x, and we got 3x. We multiplied it by 2 and we got 6. Okay, distributive property, very, very important, and becomes very, very critical in the study of algebra. So exercise 1 here starts off asking us to go ahead and determine the area of each region using the distributive property. Okay, and little did we know when we were doing area in the past, certain instances we were using distributive property, but we were. So just based on what we did on top of this, the example beforehand, we would go ahead and then we're going to distribute out the 11. So 11 times 16, and if we do that and you have maybe a calculator handy or whatever, you know that would be 176. And then 11 times 5, of course, is 55. Okay, and this, if we were to write this as an expression, or we would write it 11 and then 16 plus 5. Okay, right, and then we could, just add those two and we'd get the area of the total larger rectangle. We could do that as well. Okay, this becomes a lot easier than actually having to draw 16 units across this way, another 5 units here, and then 11 units this way. Okay, and then just counting up. Okay, we never would want to do that. All right, we want to take the easy way out when we can. They say, like in math, if you can ever be lazy, take advantage of it. Okay, take advantage of it. Okay, these example 2 here, we have A, B, C, and D. We're going to do these all together. Okay, so we're going to draw some tape diagrams and discuss them a little bit. Okay, A asks us to draw a tape diagram to represent x plus y plus x plus y plus x plus y. Okay, so let's go ahead and do that. Let's just make this x a little bit smaller than y. I don't know exactly why, but we are. There's x plus y, and then this is going to be another x plus y, and then another x plus y. Okay. All right. X plus y plus x plus y plus x plus y. All right. Now, B is a little bit different. It is asking us to do x plus x plus x plus y plus y plus y. All right, so then if we do x plus x plus x, boom, boom, and then y plus y plus y, boom, boom, and label those like this. These are all our tape diagrams, of course. These are all the same size. All the x's are the same, and all the y's are the same. They sure don't look it, but they are. Okay, so there we go. So we have x plus y plus x plus y plus x plus y, x plus x plus x plus y plus y plus y. And hopefully you're seeing something that is similar about all of these. Now we have the next one is C, and that has us doing 3x plus 3y. Now there are a few different ways. You might just take these two up here and just kind of slide them together. Okay, you could just do that. Take these and put them together, and they would look something like this. Oh, that's really bad. All right, x plus x plus x, 3x plus 3y. Okay, do that, and that's our 3x here. That's our 3y there. Okay, we could do that, or we could do it as a rectangular array, stacking. All right, which I would prefer. So I'm going to go ahead and erase all this because I want to let you know that you could do it like that if you'd like to, but we could also do it like this. We have our x and y, and we could just go ahead and do that 3 times, okay, because we have 3, and then we have x, and we have y, and if you recall, before, when we did something like this, we just did the distributive property, and we said, so 3 times x is going to be 3x, and then 3 times y would be 3y, and there we go. Okay, 3x plus 3y, which is what we have right here. Okay, using the distributive property. Or you could have represented it, similar to this, just joining these two together. Okay. Alrighty, so now D. Boy, is this exciting or what? Probably not. But anyway, D looks very similar because we've done this before. And D, if we wanted to, we have our remember our 3x plus y, 3 times x plus y. We have our x here, moving that way. We have our y here, and we know this is 3, okay? Which this is actually looks very similar to this, except that we are using these regions. Okay, these regions using the distributive property versus using a bunch of grids. Even though here we did get rid of the grid a little bit. Okay, so the first question, and probably the most important question, if you look at all these together, what do you notice about all of these? What can we conclude about all of these expressions? Because they're all separate expressions. What can we conclude about all of these? And if you use that very, very special word, equivalent, you would have been right on the money because they are all equivalent. Okay, we add them all up. We know we always have 3 x's and 3 y's. 3 x's, 3 y's. 3 x's, 3 y's, 3 x's, 3 y's. Okay? Yeah, they're all equivalent. So how are these two? How do these two? How are they? How do they equal each other? Okay, how do they equal each other? Why are they so well related? But you can see that they stacked up exactly the same. Stack of 3, and then x and y. Okay, 3 groups of x plus y right here is the same as multiplying 3 by the x and the y. Okay, which is what we did right down here. Okay, so we can see here this idea of the arithmetic, using arithmetic as we did up here, and using algebra as we did down here, and to some extent here as well. They are going to give us equivalent problems, okay, because we can write these sums up here, we can write those as products down here. Okay, so sums as products and products as sums. Okay, here example 3 we're going to also do together. It asks us to find an equivalent expression by modeling with a rectangular array and applying the distributive property to this expression. Okay, so we have the expression 5 times 8x plus 3. Okay, we are going to take that and we are going to create, firstly, let's go ahead and create a rectangular array. Okay, let's go ahead and do that, see if we remember that. The 8x plus 3 part, okay, that is the part we want to deal with first. All right, so, and again, I know this might seem a little bit confusing, but with the 8x times 3, or 8x plus 3, we can just make that 8x, because it is unknown. It really doesn't need to be, to scale, because we don't really know what the 2 actually stands for at all. Okay, so let's just say that this is 8x. This bar right here represents 8x. This represents the 3. Okay, so this is what represents what is inside the I should probably erase this, can see it very well. What is inside the parentheses right here. Okay, that represents that. Okay, now we know we have 5 of those because we have a 5 outside the parentheses. So that's our multiplier. So then we're going to go ahead and stack this up, and it's going to be 5 high. Okay. Again, we're not really worried how accurate this is, really. Okay, so here we go. We have this. Okay, and then let's just make this here too, so now we know. All right, so here's what it looks like as tape diagrams stacked on top of each other, making a rectangular array. All right, that's what this problem. So we have the 5 represented here, okay, 5 represented there, okay, and then we have our 8x represented there, okay, which is there, 8x, and then we have our 3 represented here, okay, right there. All right, now the way we want to start looking at it, though, is we want to not have to rely any longer moving forward on the grid, okay? But this is just to show you that if I do look at this right now, I can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, okay? Because what I'm doing is I am now applying the distributive property, and we're going to go ahead and do that. I just wanted to let you see that we do have 15 numbers here. So the number 15 is represented in that shaded area. But let's go ahead and just erase all of this right now. We're just going to rely on the numbers outside of the grid, which are labeling. Okay, our labels on the outside, we're going to let those work for us instead. Okay, because that's what we're going to start relying on more. It becomes more efficient, actually, and you'll see that. Okay. All right, so I'm going to go ahead and do the distributive property on the rectangular array while I do the same over here in algebraically. Okay, so I start off with 5, 8x plus 3. Okay, that is equivalent to that right there. Okay, they are the same. They're two representations of the same thing. Okay, 5 times 8x plus 3. Okay, all right, so the first thing I do is I'd want to go and do my 5 times my 8x, okay, because I'm using the distributive property now. Okay, using distributive property. And that is going to be 40x, okay, 40x. And if I did that here, 5 times 8x, here's my 40x, okay. And now I'm going to add 5 times 3, which is 15. And if I do 5 times 3 here, I have 15, okay. So I have now written and modeled an equivalent expression to the expression we began with. Okay, this here in this form much more usable, much friendlier. Let's say when we want to go ahead and then plug in an actual value for x, okay, because as this stands right now, it is nothing but an expression, okay, nothing but an expression. So until we actually plug in a value for x, the expression itself has no value, okay. So let's go ahead and let x equal 2 in this case, okay. So if we let x equal 2, we take our expression here, 40x plus 15. We plug in the 2 for every x we see here. And here we go, we have 40 times 2, because that's where the x was, plus 15. 40 times 2 is 80, plus another 15 equals 95. Okay, so that is what our expression evaluates to when x equals 2. Okay, so this right here evaluates to 95 when x equals 2. Okay? We can actually see that because we said that both this one here, this expression up top that we started with, and then this one, which is what we ended up with, were equivalent. We can test that equivalency by actually, I'm just going to erase all this right now. We can test that equivalency by actually using that original, expression up here, 5, 8x plus 3, and plugging in our 2, because we're going to let x equal 2, plugging that in up top. So we would have 5, and then we'd have 8 times 2 plus 3, parentheses, and then 5 times 16 plus 3. And if we remember PEMDAS, okay, we do our parenthetical stuff first. So we're going to add that together, and it's multiplication anyway. We do our PEMDAS first, and we have 19. And then 5 times 19 equals, guess what? 95. Okay? And you can see they are indeed equivalent. And now this and PEMDAS was very important because we did our parenthetical first, and then we did our multiplication. You can see where they end, see where they are in line here. Okay? All right, very, very important. We couldn't just simply go 5 times 16 times 3 or plus 3. Couldn't do it that way. Okay? You needed to pay attention to what we call the order of operations. Okay, and if you don't have that down yet, please, please, please make it a point to do so. Okay, for exercise 2 here, it says for parts A and B, draw an array for each expression. So we want you to draw an array for each expression like I did on this page and have been doing this entire lesson. And then apply the distributive property to expand each expression. Okay, so substitute the given numerical values to determine, to demonstrate equivalency. So what that means is this. Well, gee, let's see, there's A and B. Okay. Well, what you're going to do is, just like I did up top there, is you're going to go ahead and find an equivalent expression for this in A, and then in this in B. You'll find equivalent expressions for those. And then you're going to plug in the 5 for the x into both this original expression and then your equivalent expression. Okay? And then you're going to do the same here, but now you're going to plug in 1 for C. Use a different variable there. Okay? And again, that is similar to just what we did here in example 3. Okay, we went ahead and found an equivalent expression to that by using the distributive property, and then we went ahead and plugged in 2 for x into this expression, and also in this expression. Okay, so go ahead and do that, see how far you can get, and see what you can do, and come on back and check with me. Okay, here's A. With A, I went ahead and just distributed out this 2x plus 1, and I got 2x plus 2 after I did my array over here. Okay, I had my x plus 1 and then times 2, and I got the 2x and the 2, and you can see those match up directly over here, those two. When I go ahead and plug in or substitute the 5 for the x, as I did here, 2 times 5 is 10, plus 2 equals 12, and then I went back to the original expression, which was right here, and I just substituted the 5 in for the x, and then 2 times 5 plus 1 is the same as 2 times 6, which equals 12. So I proved the equivalency by getting the same answer for both expressions. Okay, so for this next one, B, this is B. I just went to a different page. I didn't have enough room on that other page. So I took my original expression here. Here's my original expression. Okay, right there. And I went ahead and I'm just show you the steps here of my distributing the 10. I did 10 times the 2C and I ended up with 20C. And then I did 10 times the 5, which was 50. I'm going to add those two, because that's addition in that inside the parentheses. Okay, so I have that expression. So this expression and this expression I am considering to be equivalent. Okay, drew my array here, and 20C, 20C, 50, 50 comes out to be the same. Okay, so now I'm going to go ahead and plug in or substitute the 1 for my C. And if I did that with this expression, 20 times 1 is 20, plus 50 equals 70. Okay, 70 there. And if I go ahead and plug it in up here, I could do the same. 10 times 2 times 1 plus 5. Okay, 10 times times 2 times 1, which is 2, plus 5. And so 10 times 7, which equals 70. And yes, I have proven the equivalency because they both solved out to be 70. Okay, so now for parts C and D of this exercise 2, go ahead and apply the distributive property and then substitute the given numerical values to demonstrate equivalency. Okay, again, so you're going to go ahead and use the distributive property here to come up with an equivalent expression, and then you're going to go ahead and plug in 2 for F here, and in this case you're going to go ahead and make an equivalent expression to this using distributive property. Then you're going to plug in the 10 for R in both the original expression and the equivalent expression, just like we've been doing. No need for an array this time. Okay, so go ahead and try that on your own and come on back and we'll check it. Okay, here we go. C. Hopefully yours looks exactly like this. I went ahead and distributed the 3 and got 12F minus 3. And then when I plugged in my 2 for F, I got my 2 in for F here. I got 24 minus 3, which was 21. I went back to the original expression over here and plugged in my 2, and you can see my my work there ended up with 3 times 7, which equals 21 as well. Went in and demonstrated the equivalency there. For the next one, for D, did the same thing. Did this distributive property to get to this point. Just distributed my 9 there, and went ahead and plugged in my 10 for R, positive 10. And when I did that, I ended up with negative 70 minus 99, which is negative 369. Went ahead and brought my my original equation back to check. So I went ahead and plugged in the 10 here where the R existed, and ended up with 9 times negative 41, which is also negative 369. Okay, here we have example 4, and it is a little tricky, something I want you to consider before I go ahead and show you what to do. But here we go. It has us rewriting the expression 6x plus 15 divided by 3. And that is going to look very different to you, doesn't it? Okay. Now they want us to distribute that. Okay, they want us to distribute that out. All right. How would we rewrite this using, well, I'll tell you right now the hint. Let's represent this as a multiplication distribution. Okay. What would you do? What would you use if your initial original equation tells you to divide by 3? you would multiply by, hopefully you all said it nice and loud and proud, you'd multiply by its reciprocal, which is 1/3. Okay, so we can actually rewrite this as 1/3 6x plus 15. Okay, and now we can distribute this out. Okay, we can distribute this out a little bit more, hopefully more easily. Okay, the truth is you are still dividing by 3, and you could divide by 3. But if we want to make it distributed, we talk about distributive property, we are talking specifically about multiplication. Okay, so if we go ahead and distribute it out, we know 1/3 times 6 is 2. Okay, so we have 2x plus 5, because 1/3 times 15 is the same as 15 divided by 3, which we know, which is 5. Okay, and again, if we were to look at it like this, we're multiplying, 1/3 by 15, we have 5. Okay, and hopefully this is becomes more and more second nature to you. Okay, so here we go, and that's what we have right there. We end up with 2x plus 5. Now that is what we consider, standard form. Okay, standard form. When they say standard form, they want it to look like this. We have two, not necessarily two terms, but we have separate terms, and both of those terms are combined with like terms. Okay, so they stand alone here. Here's our only x term, and here's our only whole number term. Okay, I'd like you to, let's do these one at a time, but I'd like you to try, just go ahead and pause and try to do these on your own, this exercise 3, A, B, and C. Let's go ahead and do A first. I'd like you to just do A and then come back. Okay, so I want you to use what we just did in example 4, okay, the example 4 above, and go ahead and rewrite this first expression as a sum, or also known as standard form, like we did above. Okay, so go ahead and do that, and come on back and check. Okay, well, hopefully you found that really simple. So first thing we had to do, I went ahead and took my divided by 2 and turned it into a multiply by 1/2. Okay, and distributed out just like I've been doing. We've been doing quite a bit now, and hopefully you're getting very familiar with and very fond of. And then we went ahead and did 1/2 times 2b, which is very simply b, because 2 times 1/2 is 1. Okay, and then 1/2 times 12 is where we got our 6. So b plus 6 would have been our expression as a sum or in standard form. Okay, since we've done that one, let's go ahead and have you do both B and C on your own. Pause the video, and then come on back, and we can correct those together. Okay, so here we go. Again, always just knowing these things and knowing some of these rules is such power. Just the idea that you have come to know, and hopefully to know and to understand very well, that dividing by any whole number, such as 4, is the same as multiplying by its reciprocal, which is 1/4. Okay, super. How to do that, both of these problems as well. So if I did that, I have 1/4 and 20r minus 8, and if I go ahead and distribute out, 1/4 times 20 is 5, that's where I get my 5r, and then 1/4 times 8 is where I get my -2. 1/4 times -8 actually is where I get my -2, and that's my standard form there. Same thing here. I had my 7 divided by 7, same as multiply by 1/7, distribute out, 1/7 of 49, or 1/7 times 49 is where I get my 7g, and then 1/7 of -7, or 1/7 times -7 is where I get my -1, and that's that in standard form. Okay, we're going to get back to using arrays one more time. I want to go ahead and take this expression here, 4 times x plus y plus z, and distribute it out and to create an array. Okay, the rectangular arrays that we had been doing. So, but first I'd like to just ask this question: how would you explain this expression? Let me go ahead and just erase this so you can see it better. How do you explain that? What's a verbal explanation of this expression? Okay, really important we start maybe paying a little bit more attention to what this means. And if you want to go ahead and discuss that with a parent or somebody nearby, you can, and then pause here and come on back, and we can talk some more about it. Okay, so maybe you paused, maybe you didn't. But yeah, I mean, this, to explain this verbally, what we are saying, whenever we have this multiplier in front of a parenthetical sum, okay, so a sum inside of a parentheses, what we have are this number of groups. So in this case, we have 4 groups of x plus y plus z. Okay, so we have 4 of these. That's pretty much what we're talking about. If we look up here, for example, C, in this case we have 1/7 of this group. Okay, of this right here, 1/7 of it, and you can see that's what actually happens when we take it out and we distribute it. We can see we have 1/7 of all this, and that's very obvious because now we have 7g, which is 1/7 of 49, and then we have -1, which is 1/7 of -7. Okay, so if we were to verbally explain this expression, we would say we have 4 groups of x plus y plus z. Okay, the sum. 4 groups of this sum. Okay. All right. So let's go ahead and let's just draw that up as an array. Okay. How would we do that? So again, we have our stacked this way. We would have 4. Okay. Now we have a few different elements. We have an x. We have a y, which have no value right now, and a z. Okay, x plus y plus z right there. If we distribute out, of course, we have 4 times x, that's 4x, 4 times y, that's 4y, and then 4 times z, which is 4z. Okay, and if we were to write that just numerically, we would just say 4x plus 4y plus 4z. Okay, and that is as far as we can go with that, because up here we had more numbers tied to our distribution, whereas here we have simply variables here within our parentheses as the sum. Okay. Okay, so here in exercise 4, they're asking us to expand the expression from a product to a sum, which is truly what we've been doing quite a bit already. They just want to actually tell us what we're doing now. We are actually expanding this expression from a product to a sum because it's in product form right now because we have this 3 and we are multiplying it by this sum that lays inside here. Okay, so in this case we have a product. We are multiplying one part by the other part. Okay, now we're going to actually create a make this look like, by using products, by distributing, we are going to be creating a sum only. Okay, we will have no more product to come up with. Okay, so, and the way we do that is the way we've been doing this over and over again. I'm not going to have you use an area model right now. I'm getting a little weary of the area model. If you want to make an area model yourself, you can. That's fine. I just this thing we're into 55 minutes now, and I want to get through here. Okay, so we go ahead and distribute out. 3 times the x is 3x. 3 times the 2y is 6y. And then 3 times the 5z is 15z. Okay, and there we go. We have created a sum from a product. Okay, all right. This product, this expression here, this product expression is equivalent to this sum expression. Okay, well this last example 6 is meant to take 6 minutes, believe it or not. I'm not sure where they come up with these times, but let's keep our eye on the clock here. Okay, we're starting right now at 56 minutes. So let's see if we can get this done by 62 minutes. Okay, so here it says a square fountain. Now I just want to explain this to you. It may not be as easy if you read it alone. A square fountain. A square fountain area with the side length of s feet. Okay, because we're going to actually change this. We're going to change the values of it just so we can play with it. S feet is bordered by a single row of square tiles. A single row of square tiles as shown. And here, this is the row of tiles. This is the blue, of course. So here we go. Here's the fountain. The fountain is inside. Okay, the tiles are all the blue around the edge, right? So these are the sides, the inside, these sides in here are the ones we're going to be given an actual value for, okay? So I would like you, or they would like us, to express the total number of tiles needed in terms of S, 3 different ways, okay? 3 different ways, all right? So let's start off with this. How about we say, what if S equals 4? Let's just say S equals 4. And that means 4 feet. Okay. So right now we have 4 feet here. Not S feet anymore. We have 4 feet. Okay. And we know that each one of these little tiles here is worth 1. Okay. Is 1 foot by 1 foot. Okay. So right here. This little area here is 1 by 1. We know this corner here, 1 by 1. This is 1 by 1. This is 1 by 1. Okay, we know that already. So we have those 4 tiles we need for the corners. So if each one of these sides here are 4 feet, okay, we know that that's 4 more tiles. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, oh, and 1, 2, 3, 4. So, there we go. We have drawn this in using our diagram here, our picture, and we can see that we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We need 20 tiles. Okay, and that's one way we can use to figure how many tiles we need. Okay, let's do another scenario here. How about if S equaled 2 feet? Okay, S equals 2 feet, and that's what I've drawn down here. Probably, of course, not to scale compared to the other, but now I know that the sides, these inside bits, the inside walls are 2 feet long. Okay, here are my row of tiles, my tiles on the outside. Okay, and again, I can see that I have this one little corner piece, another corner piece, another corner piece, and another corner. These are all tiles here. So I have those 4 tiles on the outside. And again, if these are 2 feet sides inside, and that's going to be 1, 2 there, 1, 2 there, 1, 2 there, and then 1, 2 there. Okay, so now I can count up, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I need, in this case, I need 12 tiles. I'd like you to think about this, and I'd like to see if you can, let's test yourself here, if you can come up with an expression that can help us solve this problem for any value for s. Instead of having to draw a diagram every time, okay, look at what we did, look at what I did. Remember the first step I took and then what I did thereafter, and see if we can come up with an expression like we've been working with in the past, and let's see if we can come up with one that'll work for any value, a value for s. Think about that for a while, give it a whirl, and come on back. Okay, so I wanted to just take you through this a little bit, and let's see how close you came to doing what I was thinking. So the first thing I did, if you remember, I outlined these corner bits, okay, and the reason, maybe you know already, but the reason I did that is because they didn't apply to the sides, because the sides that we were given a value for were inside here. Okay, these were the sides right here. All right, now I could see that those corner pieces were kind of on their own. Okay, they weren't actually, they did not have a face that met the side that we were talking about. They just had that little corner piece. Okay, so how many of those did we have? We had 4. Okay, we had 4 of those. So we had the 4 corner pieces. Now, when s equaled 4, and of course, if we have a square or quadrilateral here, we have this square fountain section here, we know we have 4 sides. So 1, 2, 3, 4. Okay, so we have 4 sides. So we have 4, let's just look at this over here. So we have 4 corners, and then we have 4 sides, and in this case we had 4 feet to a side. Okay, 4 sides, which were 4 feet sides. Okay, so that's here. All right, so then we go ahead and we look down here with the where s equaled 2 feet. Again, we had 4 corners. Okay, so 4 corners. Actually, maybe I'll do this in green. Okay, so 4 corners. Again, we had 4 sides. Okay, so these two things are staying the same in both equations and or expressions, but in this case we had s as equal to 2, so we had 2 foot sides. Okay, and so we can do this for 6 foot sides, 8 foot sides, 10 foot sides. We are always there's always a few things that are going to stay the same. And can you look and can you tell me which of those 2 things are staying the same? And that is correct. The 2 things that are always going to stay the same are the 4 corners and the 4 sides. Okay, we're always going to have 4 corners. We're always going to have 4 sides. Okay, so we could use this number because it seems like this number here, this magic number, is 4. So if we started our expression, we could say 4, and then we have sides for S plus 4 corners, okay? Because here we have 4 sides, we have the number of feet, so that's going to be the number. It's also going to stand for the number of tiles that we need to make that many feet, and then plus these 4 in the corner. Okay, all these four corner pieces, they're always going to be trailing at the end. Okay, so this is one way to write this expression. Okay, and let's prove it by plugging in some values. So let's go ahead. Excuse me. Excuse me. Anyway, let's go ahead and plug in 4 for S up here. Let's go ahead and do that. So 4 times 4 plus 4. And when that equals, of course, 4 times 4 equals 16, and 16 plus 4 equals 20. And yes, that is exactly what we got up here. If we go ahead and plug in 2 right here for our 2-foot sides, 4 times 2 plus 4 equals 8 plus 4, which equals 12, and that is exactly what we got there. Okay, so you can see in real life when you're constructing something, you're planning something such as this, a fountain or a pool with tiles all around it, to understand or come to know how many tiles you'll need. It's easy to figure out if you just use some algebra. Okay, really great way to use it. Now, this expression here, this 4s plus 4. Hopefully you also see that there is another way to express it. We could have just very simply put 4. And here we're looking at it as a sum. If we wanted to look at it as a product, we could have done 4 and then s plus 1. Okay, and 4s plus 1, because again we're going to distribute here. That's 4s, and then distribute here, and that is our 4. Okay, so this. Okay, I just went over a major, a couple of minutes long worth of a closing, and I don't think you heard any of it because you might have seen me just drawing all of this in front of you. No, you probably didn't even see that because I had turned the recording off and never did turn it back. Okay, so here I am again. Boy, what a great closing I had. Well, anyway, just the idea of my closing and that I already did was that the distributive property is going to become more and more prominent in your algebra life. Okay, we use that today to turn products, as we see here, this 4 times x plus 3, and we went ahead and turned it into 4x plus 12. We turned that product into that sum, and those were equivalent expressions in the meantime. Okay, and when we created these rectangular arrays, and when we took out all the grid work in between, we looked at this in terms of the concept of area. Okay, because we have an x, which is an unknown still. We had a 3 here, okay, and then we had 4 high right here, and that's where all of these come from this right here. This is our x plus 3. This is our 4. And if we go ahead and do the multiplication like we would in any area problem, 4 times the x gives us 4x, and then 4 times the 3 gives us 12, okay? And those, of course, correspond directly to our sum over here. Okay, and again, area is going to come up more and more. We're going to get into more, actually, quite a few geometrical concepts as we move through the rest of this module 3. Okay. Well, anyway, I'm sorry this was so long. I do wish you luck on your problem sets in the exit ticket. Any questions ever? Give me a call or email me.